you to train a machine learning model, and then how you can deploy that model as an API using PAI. So I'm here on aliyun.com. This is Alibaba Cloud's Chinese site. Some of the features I'll be demoing today are only available on our Chinese site right now, but don't worry, those features will soon go live on our international site as well. So you just need to wait a little bit, maybe a month or two, and then all of the things that I'm showing you will also be available on our international website. So you'll notice that the site is in Chinese. Don't worry, once I get into the console, I'll be able to switch over to English. So to do that, I'm going to click on this console button here, 控制台 in Chinese. I'll click on that. That opens up a new tab. We are now in the console. And from here next to my avatar, there's a little button here. In Chinese, it says simplified, which is shorthand for simplified Chinese. I will mouse over that, and then the English selection will come up. I click on English, and the console will now reload in English. So now I can go ahead and go over to Pi. That's the first thing I want to do. I want to go to the machine learning platform for AI. This one here under DT+, Machine Learning Platform for AI. I found that just by searching for PAI. That's the short name for this product. So the Machine Learning Platform for AI is often just called Pi, short for Platform for AI. I'll click on that. That will take me over to the Pi console. And then from there, I can navigate to the notebook service, which you can see here on the left-hand menu bar. So I will be using the Shanghai region today, but any of these supported regions here should work. There's 10 supported regions right now. I'm going to use Shanghai because that's near to where I am. And we'll be following along with this code here. So if you take a look on github.com, we have a organization called AliCloud-Academy. That's where the Alibaba Cloud Academy team keeps all of its examples and demo code. We have a repo there called Big Data. If I click into that, you'll see that we have some examples. We have some e-commerce sample data that's used in some of our blog articles about how to use DataWorks. We have a spam filtering example, some custom max compute function writing examples, and then the one we're going to be looking at today is this PyEAS TensorFlow example, PyEAS TF example. If I click there, you'll see that there's a README, which is a complete set of instructions for deploying and training a model. And it follows along with this blog from tensorflow.org, this tutorial. There's a tutorial on the tensorflow.org website on how to train a convolutional neural network on this image data set here called I think it's called the CIFAR or CIFAR 10 images. We'll be using this data set to train a machine learning system to recognize different classes of objects. 10 different classes of objects in this case, which are airplanes, automobiles, birds, cats, deer, dogs, frogs, horses, ships, and trucks. So it's a pretty random collection of objects that are totally separate from one another with no overlap. So for instance, automobile will not include any trucks. Okay, so that's enough on the instructions. Let's go ahead and take a look at how to do all this. The first thing we need to do before we even get into using any of this code here from our GitHub page is we need to create a new PyDSW instance. So from the DSW console, there's a Create Instance button here. I'm going to click on that. That will take me over to the Buy page for PyDSW. The first thing I need to do is give my instance a name. I'll call it JDP DSW TensorFlow. And then I need to choose my edition, individual or on sale. Just go with individual. That's the standard DSW edition. My region is Shanghai. It's pay-as-you-go. Currently, the DSW product is only available as pay-as-you-go, but there will be a subscription version later on. And then for the instance type, I want to choose GPU accelerated, and I will choose the cheapest one available. So I'll sort by price. We'll choose this one here that has 4 CPU cores and 30 gigabytes of RAM and one NVIDIA P100 GPU attached. You can obviously buy a larger instance class if you need it with up to 4 GPU cards attached, but for our simple example, this class will be enough here with the one NVIDIA P100 attached. We want to have a GPU instance rather than a CPU-only instance because that will help accelerate the training phase for our convolutional neural network, which is what we'll be using to classify our images. For the image that we're going to boot our environment from, we want to choose one of these TensorFlow images. You'll notice that there's PyTorch and then several versions of TensorFlow here. We want TensorFlow 2.3, the latest one. If we want to save the state of any files we upload to our notebook environment, then we need to attach some storage. If we don't do that, then when we stop and start the notebook environment, all of our changes will be lost. I actually don't need to save my changes because we'll only be using the environment one time. I don't need to stop or restart it. If you're going to be continuously using a DSW instance and you want to stop it to avoid paying extra for having it running, then it's a good idea to attach an Alibaba Cloud NAS file system so you have some permanent storage. But in this case, because we're doing a simple demo, we can skip that step. I don't need to set any of these other settings here like VPC or security group. I can just click on confirm order, agree to the service agreement, look at the summary, it all looks good. TensorFlow 2.3, DSW individual edition, and the instance type looks correct to me. I will then say create instance, and that will set up my environment. So that might take a minute. So we'll fast forward to the point where that completes. All right, so after waiting a few minutes, our instance is now running. So we'll go ahead and launch it. I'll click on Launch DSW. That will launch the online Jupyter Notebook environment. So I get this nice handy web IDE here where I can run and manipulate Jupyter Notebooks, Python 3 and Python 2, as well as launch terminals, text editors, edit Markdown, or even display a TensorBoard interface. So I can do a lot in here. And then on the right-hand menu here, you can see also your CPU, memory, and GPU usage. You can expand that out to get a more detailed view. I'll be using that later. The first thing I need to do is upload some of those files from my GitHub repository. So in here with this README, we've got these two Jupyter Notebook files and this config.json. I've already downloaded a copy of this big data repository to my desktop, so I will fetch those files from there and upload them into the workshop view here. I do that with the upload button, which is this little up arrow on the left-hand side here. I'll click on that, I'll select those three files, and I'll hit enter, and that will go ahead and upload them all into my PyDSW environment. So now they're there in the local environment on the local file system of my DSW instance. If I want to take a look at these from the command line, I can do that by opening a terminal from the launcher here. I'll click on terminal, run ls, and sure enough, you can see in addition to the project and snippets directories, which were already there for me, I've got my config.json, my cnn.ipy notebook, and my call EAS API IPy notebook. We need one more thing. Later on, when we're testing the EAS API, we will want to have a copy of that image data set that we're using. So we're using that CIFAR image data set. We need to go fetch that. If you look in the README file on GitHub, you'll see that there are instructions for how to fetch that with wget and then how to unpack it. So we'll do that. I'll copy that over to the terminal window here and go ahead and fetch that file. So let's do that now. It should only take a moment. It's a few hundred megabytes, but the internet connection on the PyDSW instance is pretty fast. So it should only take a few seconds to fetch that whole file. I'll then go ahead and unpack it with tar xpzf, CIFAR 10. There we go. That will unpack everything. And then what I want to do is move my call EAS API file into that new CIFAR 10 batches folder. So I'll do that. I'll move that using the command line again. And now we're getting pretty close to where we need to be. So again, if we go back to the README here in our GitHub repo, this will tell us everything we need to do. One more step we need to take before we run any of our notebook code to train our model is we need to create a model directory here. We should create it here in home admin workspace, and it should be called model. We need that because if we open this CNN notebook by double clicking on it and we go down to the bottom, you'll see that the last thing we do is save our final model into that model folder. So that folder needs to already be there. So let's go through this code. So a lot of this code is borrowed directly from TensorFlow.org. You can see the original copyright is in here and the original license. Any changes that we have made are in accordance with that original Apache license. So this is open source. Any changes we made are also freely available. Let's run through this cell by cell, section by section, and see what each piece of this code is doing. So the first thing we need to do is import TensorFlow itself, as well as Keras, which is a library that's built into TensorFlow that's going to help us train our convolutional neural network. We're also going to use matplotlib to display some of the images we're training on. So again, we're trying to train a neural network, a convolutional neural network, to recognize images of different items like airplanes and horses. So first thing I do is run this flow to this first cell to import TensorFlow and all of the other libraries I need. I'll do that. Okay, once that star disappears, then that will indicate that the cell has finished running. There we go. So the cell is done. Now we need to download a copy of this data set. Actually, we already have a copy here on disk, but rather than unpacking it all ourselves, we will get it directly from the TensorFlow datasets module. That will save us a little trouble because everything will already be nicely formatted for us. And we're also going to take each of those images, which are encoded as RGB values. We're going to take them and compress the value of each pixel in the image down into the range 0 to 1. This is called normalization. It's something that's commonly done to data before you pass it into a machine learning system. So I'll hit play, and that will start running this cell here. So you can see first thing we do is we fetch the data, then we'll go ahead and normalize it. And we've broken the data into a training set and a test set, and then we have labels for both the training set and the test set. The labels tell us what the correct answer is for each photo. So it tells us which thing, an airplane or a boat or a truck, is in the photograph. We'll need those labels to help train our model. So we've now fetched the data. We can now take a look at some of the data. So let's plot 25 of the images from the training set. So I'll click run, and that will plot out some of the images. You can see there's a frog here, a truck, a couple of horses, some boats, and let's see what else is there. There's a deer and a bird and a couple of other things. So the first thing we want to do is set up our model. So our neural network model here is going to have several convolutional layers and several max pooling layers, all using this activation function here. The input shape for the first layer is going to be 32 by 32 by 3. Why is that? That is because all of the images in this data set are very, very tiny. They're all 32 by 32 pixels. And each of them has a red, green, and a blue channel because they are color images. So it's 32 by 32 by 3 for each image input. So the first layer in our neural network needs to match the size of the inputs, which are these 32 by 32 by 3 channel color images. So I'll run that to set up our model. We've added all these layers into our model now. If I run model.summary here, that will give us a summary of each of the layers in our model and their output shape and how many parameters there are. So far, there's 56,320 parameters in the model, all of which can be trained or adjusted when we're training the model. That's quite a lot. That is why we're going to need to use a GPU to make this faster. We then need to complete the model by adding one or more dense layers. These layers are actually the layers that are going to do the final classification. The very final layer in the model should have 10 outputs. And the reason it needs 10 outputs is because that's how many classes there are. So if you go back up here, you'll notice that there are 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So our output will also need to be a vector 1 by 10. And the highest value in that output vector will be the class that we predict for the image. So in this output vector, 1 by 10, the floating point value that is the highest, that index in the vector will indicate the class that we think the image falls into. Okay, so I'll run that, and I'll summarize my model again. We now have these 2 dense layers here, which are doing our prediction. That brings the total number of parameters in our model up to 122,570. So this trainable params here, this will give you a rough idea of how computationally expensive it's going to be to train the model. This is actually still, this would be considered still a relatively small neural network model, so we should be able to train this pretty quickly. And you'll see here we run model compile to build the final model and decide what the loss function will be for adjusting the weights to these parameters. Then we run model.fit to train the model on our training data, and we'll do that 10 times. So we say epochs equals 10, and that will generate a history, or that will generate some output that gives us an idea of the accuracy and validation accuracy for the model. Running this cell here will actually go ahead and train the model for us. So this will be the longest and most computationally expensive step in the workflow, so I'd better start that now. So you can see that the first epoch is running, and the accuracy of the model here shows up on the right, so you can see if the model's making progress. I'll expand this sidebar too, so you can see that the GPU is starting to work more heavily now. It's at 35 or 37% utilization. And also you can see now that we're in epoch 4, we're getting up to an accuracy near 70%. So we're approaching 70% accuracy already on epoch 5. Let's let this run to completion. We should expect a final accuracy for the model of somewhere around 70%. Keep in mind that the accuracy on the training data is almost always going to be higher than the accuracy on the test data, which we've held back. That's because the model has seen all of the training data, but the test data is new data it's not familiar with. So any overfitting or other issues that exist with the model are going to show up when we test the model on our test data set. So the final accuracy here on epoch 10 is about 70%. Let's plot that out. You can see that we get a nice smooth curve here. So the model has been getting gradually more accurate over time, approaching to 80%, but not quite making it there. So the final accuracy is around 70%. Great. So that's exactly what we wanted. We could take this further if you wanted. You could look at the documentation over on TensorFlow.org. They have some steps for training more sophisticated models and doing more sophisticated tuning. We're not going to do that in this tutorial. We're keeping it simple. So the next thing we want to do here is take a look at some of the actual results. So seeing the accuracy is nice, but personally I like to see what the model predicted and why. I like to get a look at what the actual output would be. So we'll take 25 of the test images, try to predict their class, and then we'll display the predicted class and each of those 25 images in our Jupyter Notebook. So let's do that. Okay, so we get cat, that looks right. Ship, this boat here was misclassified as an airplane. This airplane is correct. Frog is correct. Frog is correct. Automobile, that looks good. Yes, this looks like a frog to me. Cat, automobile, airplane, truck, dog, horse, truck, ship, dog, horse, ship, frog, horse, airplane. That's not a bird, that should be a deer. This is a truck, that is a dog, not a deer. But it looks like overall the model did pretty well on the test data, so not bad at all. The final step is to output our model into that model directory. So let's go ahead and do that. I'll click run. We'll get some warnings about some of these features of Terraform being deprecated in future releases. We can ignore them for now. It looks like the model assets were successfully written out to the model folder. So we've now done everything that we need to do to train and save the model. How can we deploy it as an online API that anybody can call? That's where things get a little bit more complicated. So let's go ahead and take a look at that now. The first thing I need to do is go back into the terminal, and I want to go into the model directory and take a look at what's in there. And you'll see that there are two folders, assets and variables, and the model itself, which is savedmodel.pb. I need all of this. Those assets and variables folders contain important information about the model, like the biases or weights that are associated with the neural network. I want to pack those up with the model itself when I pass this all to the Elastic Algorithm Service, EAS. So I'm going to pack all this into a zip folder, savedmodel.zip, which will contain those two directories and all of their contents. So there we go. I've packed all of that together. Now I need to go ahead and upload that to an object storage service bucket so that PyEAS has a copy of it that it can use when it deploys my model for me. So that's my next step. So to do that, I will do EAS command 64, and I'll do upload saved model.zip, and then I add this -- inner flag. That is something you use when you're running the EAS command from inside Data Science Workshop, from inside DSW, to indicate to the EAS command that it can upload files over the private Alibaba Cloud network, because DSW lives inside that private network. If you were running the upload command from your own local computer, you would not include that flag. You would leave that out. But I'll use it, -inner. Oh, excuse me. So one of the things it's complaining about here is it wants to have a access key. so that it can access object storage service for me. Let me make sure that that's the problem. Okay, yes, so it looks like it needs an access key. So let's take a look at how you can set an access key. If you get this error, it's not a big deal. All you need to do is go over to the, go over to the RAM console and set up an access key. So let's do that now. So I need to go back to the console homepage, navigate over to RAM, and we will create a new user with a new access key attached that has full access to OSS. So under users, I'll create a new user. I'll call him DSW user. I will give him programmatic access, which means he has an access key attached. I need to actually receive a text message. When you do something high security on the aliyun.com website, you have to receive a verification code so that the system really knows it's you, the administrator, doing this. So I've done that. Now I have an access key ID and an access key secret that I can use. I need to add some permissions to those to give them access to OSS. So I will do that. So now I have permission to access OSS, and I'll be using this access key ID and secret. So if we go back and look at the EAS command, you'll see that it has some flags to add an access key ID or string. So I can do EAS command I, and then I'll throw my access key ID in there, which is this first value, paste that in, and then I'll throw my secret key in after the -K flag. I'll paste that in. Whoops, and then I need to actually specify config as well. I should have included the word config. So the configuration is now saved to .eas/config. That's the default location in my home directory. Now that we've done that, I can go ahead and upload this saved model. So let's do that. Whoops, I forgot the upload keyword, my bad. So we'll throw in upload there. And now we have uploaded it. And we're going to need these two values. We're going to be putting those values into this JSON file, config.json. This config.json will be used by the EAS command line tool to create our EAS endpoint for us. So I'll right click on config.json and choose open with editor. That will open up a text editor window. I need to throw the model path in here and the OSS endpoint in here, so I'll do that now. The rest of this I can leave alone. This metadata section at the bottom says that EAS should deploy one container to serve the model, and it needs one CPU core. We actually don't need a GPU to do inference, to do predictions, because it's not as computationally intensive as training the model. And then the only two parameters in here I need to change are these two. I could also change the name of the EAS API deployment if I wanted to. I'll just leave this default name in here. So for the model path, that will be this second value here that starts with OSS. Whoops, let me copy that to the clipboard. Go over here, replace that. So this is the path to my OSS bucket, ID number, and then save model.zip, which is where my model lives. And then I need to replace the OSS endpoint, which is this first value, but note that you don't need to include this HTTP part. That is optional. I really only need this part here, starting from OSS and ending with .com. So I'll fetch that, plug it in, save my changes. I just hit Command S or Control S to do that, but you can also do it from the File menu. And now I can close that config.json. I don't need it anymore. Let's clear the terminal. And my next order of business is to actually go ahead and deploy this thing. So to do that, I do EAS command 64 create, and then config, I'm still in the model directory. I need to go back up one. There we go. EAS command 64 create config.json. And then I just hit enter, and that will go ahead and start the configuration process. And this is going to set up my endpoint for me. The information I really need to use that endpoint is already at the top here. I need this internet endpoint and this internet endpoint and this token. If I'm calling my API from within Alibaba Cloud, the internet endpoint is this one. If I'm calling it from over the internet, I'll use this top endpoint here, which is a public endpoint. And of course, when I make a request, I have to sign it with this secret key. If I don't include that token, that signing token, then my request will be rejected. That's because I don't have my API set up as a public API. By default, it's a private API to keep it safe and protected. So if you'll remember, we moved our API test code into this CIFAR 10 batches folder, which is where all of our test data is. So let me go in there and open up that Jupyter Notebook. And you'll notice as you look at this, it's got some helper functions to remind me what the classes are in the image data set. It's got some code to help me read in the image data sets here, which are packed up as Python pickles. So they're binary files. It's got some code to help me reformat those into NumPy arrays and then get their labels. And then at the bottom, it's got some code here to actually make a series of API requests against my EAS API endpoint. I'm going to use those API requests to test that EAS is running and that my model can actually make live predictions over the internet. Before I do that, I will need to make some changes to this code. So let's see how our deployment process is going. It looks like it's almost done. I just need to give it a few more minutes to finish. Once it's done, I will run a curl command like this one here, where I replace path to API endpoint with the API endpoint from up here, and I will replace this authorization code with my secret token also from here. And you know what? I need to plug both of those values into my Python notebook as well. So let me copy both of those to the clipboard, and then I'll go ahead and paste them in to call EAS API. So my URL should be, my secret token should be this, no space at the end. The double equal sign is important. Always keep that part. That's my authorization code, my token. And the URL should be this one here, this public endpoint. I want to test the public internet endpoint rather than the private one. Okay, I have thrown that in. It looks like it's okay. I don't see any major problems with that. Simple image rec test looks good. And then let's see, have we finished our deploy? Yes, it says service is running at the bottom here. That means that our Pi EAS model is now running. And in fact, if I were to go back to Pi, so leaving RAM for a moment, if I were to go back to Pi, I would see here under EAS model serving that there is a model running under that name. And you can see it's a 1 CPU single instance deployment. And here I can go look at the monitoring dashboard and see if any API calls have been made or anything like that. And I can look at service logs. I can see the list of currently deployed instances, which are actually Docker containers. And all of that is available under the monitoring dashboard here. Going back to the terminal, I want to go ahead and run that curl command I was talking about. So I want to do this. I want to plug that URL in to my curl command here, and then plug the authorization in and then see what the output is. I need to take a look at that output to figure out how to use my model. So let's temporarily make ourselves a new text file. I'm going to copy and paste this over from the comments here. I need to replace this with my endpoint. So we'll grab the endpoint URL here. Let's do that real quick. So I'll grab the endpoint URL, paste that in here. Wonderful. Now I need to grab my secret token. Again, paste that in here. And now I can go ahead and run this curl command from the terminal. So let's do that. So I'll run that, and you'll see that what I get back from the API endpoint is this response, this JSON response. That vertical bar JQ at the back here, that just makes this color-coded nicely and formatted nicely so it's easy to read. If I left that off, I get something like this, which is a lot harder to deal with. I just wanted to make everything be formatted nicely. So you can see here, the things I need to pay attention to are the input and output sections, particularly the inputs. So the output tells us what the model is going to send back to us. It's going to send us back a 1 by 10 array called dense1 of type float. So that will be the output from the final layer in our neural network. The input is going to be called con2d input, and it will be a 32 by 32 by 3 image, also of type float. So to actually make the API call, we need this information. You'll also notice we need help from a special library here. We have this tool called tfpredictpb2 that's coming from PyTFPredictProto. So this is a library that actually serializes the inputs to PyEAS. So PyEAS provides us with a standard HTTP RESTful API, which means we need a way to turn our 32 by 32 by 3 array into a flat string of characters that we can patch or that we can pass over in an HTTP request. So to do that, this PyTFPredictProto protocol buffer tool is going to help us. But it's not installed yet. We actually have to install it ourselves from the terminal here. So that's the final thing I need to do before I can start testing my API. I have the install command listed here in this README. So let's go down here and find it. Here it is, pip install. This is the command I want. Paste that in. Now we'll go ahead and install that protocol buff tool for us. Now I can run everything in this notebook, it's all in one cell, just by restarting the notebook and running all of it. So I'm going to restart my notebook because the notebook won't be able to see this new Python library until the kernel for the notebook has been restarted. And if we scroll through the notebook quickly, you'll see that it has some helper functions and a list of the classes from the CIFAR10 dataset. And then it also has a function at the end that goes through the first 25 images in the test batch from that data set, the test images. It goes through the first 25 images, reformats the data into a 32 by 32 by 3 array, normalizes it down into the range 0 to 1, just like we did when we trained our neural network. Then we build this serialized request, and we insert some values into there, into the input section in the request. Remember, we need to build a structure that looks like this input here. And then finally, we take our image and we reshape it down into a single 1 by 37.2 array. So we reshape it into a single flat array. So 32 times 32 times 3 equals 3072. So we're flat packing it so that we can serialize it and pass it as an HTTP request. What we need to do is change a couple of these fields here. So this serving default here at the top, that signature name should match the signature name in that response we got back from curl. In the input section, the name in the input section, conv2d input, that's what should go here. So I need to delete that 6 and make all of these 3 lines of code read conv2d input. And then we're setting the type to dt float, just like we have here. We're setting the shape to 32, 32, 3. In this case, 1, 32, 32, 3, since we're passing in one image at a time. We could make that 2 or 3 or 4 if we were passing in multiple images. And then the float value itself is going to be our flat packed image data. Then we serialize our request into a string so that we can make an HTTP request. We include the URL and headers in here, and then we use the Python requests library to make a post request to that URL, which is our EAS endpoint, using our secret token, and the data is set to the request data here that we got by serializing all of this into a string. And once we've done that, we will get back a response. We need to call predict response on our tfpredict.db2 module to create that response body parser. We pass into that the content of our HTTP response. We then do some magic to yank the floating point values out from that response. So remember, the response that comes back is a string that's in basically JSON formatted. We need to pull out all of the sections that say float value. And specifically, we want the number that comes after the float value tag. There should be 10 of those, since the response is a 1 by 10 array. We convert those 10 float values back into floats. They're strings at first, because all of the data that we get back from parse from string is string data. We look for which of those float values is the highest, and then we map that onto the classes list from up here to figure out what our model predicted the image was. Then we print out the predicted class, the class the model thought the image was, its actual class, and then a picture of the image so that we can do a quick sanity check. Okay, so let's run all that. So I'll click restart. That will go ahead and run this whole notebook, and you can see that we were able to successfully call the API, and we can see each image, its predicted class, and its actual class. So you can see, for instance, this is a ship, but we predicted it was an airplane, so that's a mistake. Most of them are right. There are a couple of small mistakes in here. For instance, let's find a mistake. Looks like most of them are right, actually. This is doing pretty well. Oh yes, we thought this was a bird, but it's obviously a deer. And then we thought this was a deer, but it looks to me like it's a dog. So there are 2 or 3 mistakes, but overall, the model did a really good job. And then if we were to go back to the model serving interface here, we may even be able to see some of those API calls taking place. So you can see that if we look at the queries per second, there was a slight uptick here when we made 25 or 30 calls to the API to run our code just now. And that's it. So we were able to train a simple model to achieve 70% accuracy in classifying images into 10 different classes. We were then able to save that TensorFlow model, upload it to PAI, and deploy it automatically without writing any additional code as a HTML, or excuse me, an HTTP API. So we were able to turn our trained TensorFlow model into an HTTP RESTful API in just about half an hour. Not bad. And that's it. That's it for the demo. So at this point, all we would need to do is delete our model, which we can do from the PyEAS model serving console here. And then we log out of our DSW environment, click leave, log out of that environment, go back to the notebook service. You can ignore those network errors. And then we'd click delete and hit OK. And that would go ahead and delete our environment, and then we won't pay any more money to run it. We're all done. And that's all you have to do to deploy a model with EAS after training it with DSW. Thank you for joining me, and I hope to see you in a future talk.
Great. I think I'll be able to take it away from Jeremy here. Thanks everyone for joining us today. I think, Jermaine, I'm fine just picking it up from here. Thanks everyone for joining us today. Thanks Jeremy for that demo. It's really cool what we're able to do now with this really simple, actually very simple way to put machine learning algorithms into just analyze simple pictures, right? Now, once again, these pictures that Jeremy was looking at today were actually quite small. Here, I'll say hi to everyone. We're just little thumbnails. If you guys looked at the database yourself, hi everyone. If you go look at that database yourself, you'll see that those pictures are actually quite small, just so you can deal with so many of them. So as you begin to scale and start to look at bigger pictures, you'll realize that there is sort of a bottleneck at storage and the amount of data you guys can transfer at one time. And that's something to think about as you create your databases for your machines to analyze. So what I wanted to share with you guys today, let me see here. Bang, share. I think everyone can see my screen now. Was some just a little bit deeper on the outside of what Jeremy was talking about today. Not only just the layers of computer vision, which is what Jeremy was focusing on, and computer vision is sort of the output of the machine learning models that we're talking about. The layers of computer vision, but then also some other applications. So you guys can think about how image search can be seen more around you. Cool. So on the most basic level, we had the image classification. Okay. So on that level, you just identify that a certain object is in the image. And that's what we were doing today. We were looking at a whole thumbnail, such as this picture of a cat. And we were saying, okay, within this entire image, including the ground, including the grass, including everything behind it, there is a cat. Okay, so that's what we first want our machine to be able to do. Next is we want the machine to tell us where the cat is in the picture, right? And this becomes useful when you are trying to locate different things in the picture, right? If you look at picture tagging now, you can see object localization when there's multiple people in the picture. It can say this person is this person, and this person is this person. Google Photos, Facebook Photos, I'll do that. So that is the second layers for your machine to be able to put a box around what part of the image it recognizes it as cat. And then that sort of leads to object detection, right? And that really comes into when there are different objects within an image that you're trying to identify, right? So like in Jeremy's example, it's a very one-dimensional case where you're just trying to identify one thing in an image. But it's more useful to identify pairs of things in the image, right? So within this box, in this red box, there is a dog. Within this green box, there is a cat, and there's this clear space between them. And so within the image, we're now detecting, and then we're segmenting. And then the sort of the next level that we get to when we get to segmenting is drawing more precise lines around the objects so that we can, within that image that we have, we can see more of other things. You can imagine that if in the image on the left, there were other things within the dog's box, say above his right ear, we wouldn't be able to detect it as well because it was sort of within the dog area, same with the cat. But on the right image, you can see sort of like when you cut something out in Photoshop, we're getting a very precise area of where both the dog and the cat are, so that if there is something, say, between the dog and the cat, or a little bit above the dog, a little bit above the cat, we would be able to catch that as well, detect it, and segment it from the dog and the cat. And some other things that we've been seeing around that are getting popular, and certainly platforms like Instagram and other social media apps are using cool filter ideas to enhance images and make them more interesting. We now have, as you can imagine, taking a bunch of images and searching through them. We can now also add images to current images through similar algorithms to create new images. And this is done through the process of inputting many, many images into this sort of style image and getting output images that are interesting and something that we find to be sort of a third unique image. So here's an example of the same image, the content image, and then sort of added a style image, right? So these are some famous, we have the Starry Night, we have the Scream, and then we have Sandy Beach. We have the same image, and then we're getting this output image, which is some combination of them, right? And so we want to keep sort of the style images fairly consistent. Those are the popular images, and then be able to change the content image to a user inputted image, and then give that user an output image of their input image that is interesting, or sort of stylistic, if you will. So that's another use of this application. And in similar ways, we can take thousands of images and get an idea of what images should look like based on previous data, right? And the neural network now says, okay, not only can I identify what a beetle or what a house looks like, but I can even reconstruct a broken image to make it look like what I think a house, a beetle, a waterfall, or this woman might be. And these examples here are done really well. I wouldn't expect sort of a machine with just tens or even hundreds of thousands of images to be able to reconstruct images this well. But you can sort of imagine once the machine has the neural network has a good idea of what these things should look like, they'd be able to reconstruct broken images. And these example broken images are a little, of course, exaggerated too. Someone just took a white paintbrush over some perfectly fine pictures. But you can imagine that if someone were to photobomb a picture, or there were to be some weird light, or something you'd want to be taken out of a picture, this image reconstruction might be able to help. If the user is to identify a part of the picture that was broken, then the software could repair it. And if the user was able to then input that data every time to the software, so the software could learn what the user thought was a broken part of an image. Maybe the machine itself could learn what a photobomb was, right? And then that would be super interesting, right? You could give it a series of pictures to take out the person photobombing all the pictures. So that's something interesting. And sort of the last one that I had, sort of on the crazier side of things, is a full reconstruction of images, right? And this really teeters on recreating images to the point of unable to recognize the original. And I think a very simple example where there's just a sort of a color change is zebras and horses. You can see here that after this computer saw thousands and thousands of pictures of horses, it was able to take a zebra, recognize the shape of a horse, and then say, oh, I know where the colors should belong, based on the shadows and where the light's coming from. I should know where the colors of a horse should belong, and output something like that. Similarly, that same machine might have thousands and thousands of pictures of zebras, and be able to take a horse picture and say, wow, that looks a lot like a zebra. Let me put on it what I think a zebra might look like, right? And you can see that this computer did a pretty good job. You can see some sort of wavy parts on both of the recreated images, but certainly a good effort. And if you saw that second picture first, you might even be fooled, right? Cool. So that's all I had today. I just had a quick short presentation about just building on some of the things Jeremy had to say. Wanted you guys to have a better idea of how deep this image searching goes and how much more complicated it gets with each layer. Certainly being able to tell a certain object in an image is easier than the next two steps of being able to draw boxes around an image, or even be able to distinguish its images within an image. This takes a lot larger data sample and a lot more rigorous neural network to be able to handle this at a lower error rate. And on top of that, you guys can also think about the way image search is being used in other ways to be useful, whether it be to make work tasks easier. For example, being able to read handwriting. Handwritten notes can be transcribed into text, or it is analyzing pictures, or being part of a creative design department where you need to create a look of a company. And maybe it's a machine that can create that look for a company, being able to feed in several different images and it creating a certain style for you. Or just, as far as image manipulation, and then also image identification. I think there's a lot of places to go. And we hope that Alibaba Cloud PAI's platform is sort of an easy place for you to get going on these. Feel free to watch this video again. It will be available online. To watch Jeremy's demo again. I'm sure you might need to watch that 2 or 3 times to be really comfortable with that whole process. But don't worry, I think it is very able to be done. I've gone through it myself, and I find it, it's nice that we have a place that is actually quite user-friendly to build such a complicated machine learning or deep learning algorithm. So we thank Jeremy again for running us through that demo. We thank everyone here for watching. I see that we don't have any questions at this point of the video. So I can wait a few minutes here to see if you guys have any questions. And if not, then we'll just we'll end it here today. And thank you guys all for watching. Hope you guys can jump into the PAI platform soon and direct any questions about your experience or comments about your experience. We love to hear stories about your experience. You can direct those back to us. And we'd love to continue to interact with you. Okay. Okay, so we have a question about a certificate. We actually have a machine learning learning path that I would like to share with you guys now. Let me just pull up the link for that. It's great. It's 8 courses. It's 8 courses on machine learning that does come with a certificate after you complete the 8 courses. It does talk mostly about PAI, which is what we've been talking here today. Here is that course. That's the machine learning course. Feel free to take the entire course package if you want that machine learning certification, or take any of the courses within the course. I think there's very good ways to do that. Yeah, I mean, facial recognition algorithms are usually built and kept pretty private by companies that are using them. There's not a lot of open source facial recognition algorithms to be used. That being said, you know, there's similar ones, right? Like, you know, analyzing a dog or a cat. I mean, these are the foundations for analyzing a human face, right? Obviously, there's a lot more details for a neural network to analyze in a human face to be more positive that is human, right? So for a dog and a cat, right, we see a dog nose and a cat nose, and we say, you know, that's very easy to tell, you know. But you see, you know, a group of humans from a certain ethnical tribe, there's very subtle differences between them. So our neural network needs to be a lot stronger, and that needs to be built with some mind into really what features on a human face do make people different, and that takes a lot of thinking by the designer. Yeah, good luck with that, Marisol. That is something the top tech companies in the world are working on right now. And if that's something you want to dive into, it's certainly a brave field to go into, but it is a difficult one. Yeah, great. All right, I'll keep it open for a minute or two if you guys think of any questions. And yeah, I think Jermaine, there will be a copy of this webinar people can watch later, right?
Yep.
I think that will be available somewhere.
Yep, that's right. So
Okay.
Once we have posted the webinar onto YouTube, we'll email you the link to watch.
There it is, YouTube.
Yep. Anyone has any other questions for James? Alrighty, James, I
Cool.
think we can call it a
Great.
day.
Great. All right. Thanks everyone for watching. We'll see you on the next episode.
Yep. Thank you so much, James. Thank you,
All
everybody.
right. Bye, guys. Yep.
Have a great day.
Bye now.
Bye.